In this tutorial, I will be covering how to use both BJT and MOSFET transistors for the purpose of switching power. Modern transistors come in two flavors: bipolar junction transistors, or BJTs, and field effect transistors, or FETs. Transistors come in multiple package types, common ones including TO92 and TO220. Both BJTs and MOSFETs come in these packages. First, we will talk about BJTs and feature them in the TO92 package. In this package, pin 1 is the emitter, pin 2 is the base, and pin 3 is the collector. There are two types of bipolar junction transistors, NPN and PNP. Note the direction of the arrow to differentiate the two transistors in the circuit symbol. An easy way to remember which is which is the phrase "not pointing in" for NPN. The internal workings of these transistors are beyond the scope of this tutorial. Instead, I will show you how you can use these practically in a circuit to switch power with an input, starting with the NPN transistor. Here I have a simple circuit to power a small motor with 5 volts and an input. The input could be provided by a device such as an Arduino or Raspberry Pi. The transistor is like a switch. We connect our I/O to the base. With the NPN transistor, current flows through the collector out the emitter when the base has voltage applied. In this circuit, when we apply 5 volts to the base of the transistor, we effectively close the switch, allowing current to flow from the collector to the emitter. Note that a small amount of current flows from the base to the emitter. This is why we have a current limiting resistor on the baseline. If we didn't have this resistor, we would allow too much current flow between the base and emitter, which would result in a fried transistor and potentially damaged controller. When the switch is closed, current is allowed to flow from our 5 volt supply through the motor and then to ground. Our motor spins when this happens. If we were to remove the 5 volt input voltage on the base, current flow between collector and emitter would stop, thus stopping current flow through the motor. The flyback diode prevents a voltage spike forming when the motor winds down by allowing reverse flow of current. The motor is a load in this circuit. Note how we have a 5 volt or high side of the motor and a 0 volt or low side of the motor. The NPN transistor is on the low side of the load. Why? Because for us to close the switch, we need a base emitter differential of approximately 0.7 volts. In this circuit, our base is at 5 volts and emitter is at 0 volts, yielding a differential of 5 volts. Since 5 volts is greater than 0.7 volts, we close the transistor, allowing current to pass. So now it should make sense as to why when we apply 0 volts to the base we don't get current flow. In this case, both base and emitter voltages are at 0, yielding a differential of 0, and since this is not greater than 0.7 volts, we do not get current flow. This has been a simplified explanation of how to use a BJT. We still need to go over how to spec out a BJT. After all, how do you spec out which transistor to use? How do you pick the right current limiting resistor? Choosing the right components depends on what you're trying to do. I'll continue to use the motor circuit example. Let's assume our motor is a 5 volt DC motor that draws 75 milliamps. Let's assume we're trying to control the motor with an Arduino Uno. An Uno could safely deliver 5 volts DC up to 20 milliamps. Now let's spec out our parts. Our criteria for the transistor is therefore one that has a collector emitter voltage maximum of 5 volts DC or more, can allow 75 milliamps between the collector and emitter, has a base emitter voltage maximum of at least 5 volts, and we can shoot at least 20 milliamps between the base and emitter. The 2N2222 is a common NPN BJT. The datasheet indicates a max limit of 40 volts DC allowed across the collector and emitter, and this is greater than our needs. As well, we can shoot up to 600 milliamps through it. The emitter base voltage tops out at 6 volts DC, and this is fine for our application. Now let's look at the gain of the transistor. The way BJTs work is that the amount of current allowed through the collector is dependent on how much current we shoot through the base. The transistor is like an amplifier. More base current reduces impedance through the collector, allowing more current flow. Taking a look at the datasheet, we see a few DC current gain values depending on certain conditions. We want to shoot 75 milliamps through the transistor. The datasheet gives an example at 150 milliamps through the collector when collector emitter voltage is 10 volts DC. This yields a gain of 100 to 300. That means that for our situation, we are looking at a gain likely somewhere between 100 and 300. A huge range, I know, but this is what they're telling us. With our circuit, we want to shoot 75 milliamps through the collector, so let's do some math. 75 milliamps divided by 100, which is our gain, minimum, yields 750 microamps, meaning we need to shoot a minimum of 750 microamps through the base of the transistor. This is less than the max output of the Arduino, so this means this transistor is fine for our needs. Using the formula V equals IR, we can calculate the current limiting base resistor we need. R is equal to V over I, V is 5 volts, I is 750 microamps, therefore a 6.5 kilo ohm resistor would work. If we used a smaller impedance resistor, it too would work and would allow for a margin of error in calculations. Our upper limit of the Arduino is 20 milliamps. Using the same formula, we can see that our lower end resistor we could use is 250 ohms. I'll choose a 1 kilo ohm resistor. This will allow for 5 milliamps through the base. Alright, so we have a transistor and a resistor. The last thing we need to consider is heat. Transistors aren't perfect conductors, and so it is expected that they'd warm up during operation. But just how hot will it get? The datasheet indicates a temperature increase of 200 degrees Celsius per watt of power dissipated, so therefore we need to calculate this power dissipated. Voltage drops occur across both the collector and emitter as well as the base and emitter. We should expect about 0.3 volts drop across the collector and emitter where we have 75 milliamps of current flow. This means we're dissipating about 22.5 milliwatts of power. We should also expect a 1 volt drop across the base and emitter with a current flow of 5 milliamps. This yields a power dissipation of 5 milliwatts. This totals up to 27.5 milliwatts of power dissipation. When we multiply this by 200 degrees Celsius per watt, we get an expected temperature increase of about 5.5 degrees Celsius. This is low enough to not warrant the need of a heatsink. When I hook the example circuit up and take measurements, I see that indeed we do get about 75 milliamps current draw from the motor. When I switch to measuring voltages, we see that we get a voltage drop across the collector and emitter of 0.05 volts, which is less than the 0.3 volts maximum the datasheet specified. Across the base emitter, we get a voltage drop of 0.76 volts, and this is within the expected 0.6 to 1.2 volt drop the datasheet indicated. This means our transistor is dissipating approximately 7.6 milliwatts, which should equate to a temperature increase of 1.5 degrees Celsius. Now it's at this point that I should bring up how my circuit is not actually complete. We should have a pull-down resistor on our baseline. This high impedance resistor pulls the base to 0 volts when the I/O is floating. Why do we want this? If we were to power the 5 volt line and neglect to connect a controller I/O, is the base high or is it low? It's really left floating, and in this state, static buildup, noise, or leakage could potentially allow for collector-emitter current flow. This can lead to unsafe situations. So there you have NPN transistors. Let's take a look at its sister, the PNP transistor. Here I have a similar circuit, this time using a PNP transistor. Note the same base resistor, motor, and flyback diode. With the PNP transistor, current flows from the emitter through the base and collector. In this circuit, 5 volts would flow from the emitter to our I/O through the current limiting resistor. So when we apply 0 volts to the transistor, we get current flow. This in turn closes the switch to allow current through the motor. We are seeing a lot of similarities between the NPN and PNP transistor here. Just note that the PNP is on the high side of the circuit, that is the side before the load. This is an important distinction between how you use NPN and PNP transistors. NPN are low side, PNP are high side. Let's look at the math. While the NPN transistor needed a 0.7 volt base emitter differential, the PNP requires a negative 0.7 volt differential. When we apply 0 volts to the base, we get this. In this case, we have a negative 5 volt base emitter differential. When we apply 5 volts at the input, our differential changes to 0 volts. This is not below negative 0.7 volts, and thus we restrict current flow through the transistor. It's important to note that this negative 0.7 volt differential is always achieved when we have a 5 volt input and a 12 volt supply to the switch. This situation may happen when we are using a 5 volt device such as an Arduino to try and control a 12 volt motor. Sure, a transistor is closed when we apply 0 volts at the base. After all, we have a differential of negative 12 volts. However, if we apply 5 volts at the input, we achieve a base emitter differential of negative 7 volts, which is still way below negative 0.7 volts. This means that we get current flow at 0 volts and we get current flow at 5 volts. We have two transistor states, closed and closed. You won't be able to stop current flow in this simple circuit. Now again, similar to before, this circuit is incomplete. We should be including a pull-up resistor on the base of the transistor for safety reasons. This time we are effectively applying 12 volts to the base when the I/O is floating, which keeps the transistor open. Here I've built up two demo circuits using both types of transistor. On the right is the NPN transistor. When I apply 5 volts to the base, the motor starts to spin. When I remove 5 volts, the motor shuts off. When I apply 0 volts to the base, the motor stays still, and again 5 volts turns it on. Now I am rewiring the motor to connect it to the PNP transistor circuit. When I apply 5 volts to the base, the motor stays still. When I apply 0 volts to the base, we get the motor to spin. 5 volts again keeps the motor still, and again 0 volts winds up the motor. That's it for BJTs. Now let's talk about the MOSFET transistor featured here in a TO220 package. Again, we have 3 pins and a tab on the back. Pin 1 is the gate, pin 2 is the drain, pin 3 is the source, and the tab on the back is connected to the drain. MOSFETs have their own symbols shown here. Similar to BJTs, MOSFETs come in 2 flavors, N-Channel and P-Channel types. Note how the direction of the arrow in the symbol tells the 2 MOSFETs apart. Now let's look at using the N-Channel MOSFET. Here I have a circuit similar to the NPN BJT. We have a motor, flyback diode, transistor, gate resistor, and pull-down resistor. Again, the I/O can be a device such as an Arduino or a Raspberry Pi. Our pull-down resistor pulls the gate low when it is otherwise left floating. When we apply 5 volt to the gate, we build up charge on the gate. Unlike a BJT, current does not flow through the transistor. So why the gate resistor? The gate and source act like a capacitor, thus we build up charge on the gate. Building up charge is current flow, if but for a brief moment. The resistor on the gate limits this flow, protecting the controller. When 5 volts is applied to the gate, we allow for current flow from our 5 volt supply through the motor into the drain and out the source. Similar to the NPN circuit, the N channel is on the low side of our load. Looking at the math, we have a gate voltage of 5 volts and a source voltage of 0 volts. Our gate source differential is therefore 5 volts. Different MOSFETs require different voltages to operate, and 2 volts is the upper minimal limit for the MOSFETs that I have used. A higher gate source differential will yield a higher conductivity between the drain and source, lowering internal resistance up to the maximum rating of the MOSFET. Check your datasheet for more details. So N-channel MOSFETs are used in situations similar to where NPN BJTs are used, on the low side of the load. N-channel MOSFETs tend to be easier to acquire, similar to NPN BJTs. Now let's say we're trying to spec out a MOSFET to switch this motor on and off using an Arduino. The same functional requirements need to be met where we need to switch 75 mA of 5 volts with a 5 volt input. I happen to have an IRF3205 sitting on my desk here. Is it a suitable MOSFET? Let's take a look at the datasheet. We see in the maximum rating section that the MOSFET can allow for a continuous drain current of 110 amps if it is kept at 25 Celsius. We also see that the device can tolerate up to 20 volts between the gate and the source. Page 2 shows that the device can tolerate up to 55 volts minimum before it starts to break down. All these parameters are overkill for what we need. MOSFETs differ from BJTs in a few ways, with one way being that current does not flow from the gate to the source like it did in a BJT between base and emitter. Instead, the gate is charged with voltage to allow current flow between drain and source. As voltage increases at the gate, impedance is produced between drain and source, allowing for more current flow. BJTs amplified current by using current. MOSFETs amplify current by using voltage. More voltage means more current flow. This is actually described in the datasheet using a graph. Here we have several lines that are indicating drain source current dependence on both drain source voltage and gate source voltage. Notice how as the gate voltage increases, the allowed current between the drain and source increases. We will be applying 5 volts to the gate with a drain source voltage of 5 volts. According to this graph, this should allow up to 30 amps of current through. So we know this transistor will work for our circuit. Now what about the resistor? Well again, if we're using the Arduino, we're limited in how much current we could deliver. Earlier I calculated that a 250 ohm resistor would limit current flow to 20 milliamps. I could use a 1 kilo ohm resistor though. This would increase how long it takes to charge up the transistor. For most applications, we don't need to worry about this. It's typically faster than we can perceive. If you are concerned about it though, you need to be aware that the gate builds up charge and calculations need to be made to determine how long it takes to build up the appropriate charge for conductivity between drain and source. The last thing we're going to want to consider is again heat. The datasheet indicates a thermal resistance from junction to ambient of 62 degrees Celsius per watt of power dissipated. How much are we dissipating? This depends on the drain source resistance, and the datasheet identifies this to be a maximum of 8 milliohms. The power calculation is easy. Power is equal to I squared R. Plugging in the values, we see we dissipate 0.0045 milliwatts. This, multiplied by our thermal resistance, yields an expected temperature increase of less than a degree Celsius, so therefore we shouldn't have to worry about a heat sink in this case. But enough about N-channel MOSFETs. Let's look at the P-channel MOSFET. Here I have a similar circuit as before, including the I/O, gate resistor, pull-up resistor, the transistor, motor, and flyback diode. The pull-up resistor pulls the gate up to 5 volts when our signal is left floating. When we apply 5 volts to the gate, we do not get current flow between the drain and source. When we apply 0 volts to the gate, we again build up charge at the gate, thus warranting the current limiting resistor, and we increase conductivity between the drain and source. This in turn allows current flow across the motor. This happens because we have a negative gate source voltage differential of negative 5 volts, which is less than our required minimum of negative 2 volts. So there you have it, how to use either a BJT or MOSFET transistor to switch power using an input from a device, such as an Arduino or Raspberry Pi. For more tutorials like this, visit thezanShow.com.